Hello, and welcome to this MCA webinar, Servo Solutions for Mobile Automation Challenges. My name is Liz Wright, and I'm the Marketing Manager for the Motion Control Association. This webinar will be recorded, and a link to the recording will be sent to you within the next 24 hours. If you have any questions, please submit them in the questions panel of your webinar screen, and we will answer them at the end during the Q&A section. Any additional questions will be answered via email after the webinar has concluded. I'd now like to introduce our presenter for today's webinar, Shane Bielke from Advanced Motion Controls. An executive team member, Shane has been with Advanced Motion Controls for over 8 years and provides corporate direction for product strategy and product development efforts. His background and extensive product and industry knowledge comes from nearly 20 years of direct experience in the motion control industry. Shane's direction for delivering the best possible servo drive solutions available in the market has roots from his background and investigations of both industrial trends and future product needs. Having previous functional responsibilities as a product engineer, product manager, strategic planning manager, and in international sales, Shane has grounded experience of providing direct products to customer needs. His deliverables have remained not just strategic, but on target. Shane's education includes a Bachelor's of Science in Electrical Engineering from the University of Minnesota and a Master's of Business Administration from St. Thomas University. Shane is a member of the Association of Unmanned Vehicle Systems International. He has contributed on several technical articles and given presentations on a variety of technical subjects. I'd also like to thank our sponsors of today's webinar, Advanced Motion Controls. This year, Advanced Motion Controls is celebrating 27 years of proudly supplying high-performance servo drives designed and built in the USA. Over 1.5 million servo drives, accounting for over 2.5 million axes of motion control, have been delivered to date. The company was founded in 1987 and incorporated in 1988 with the idea of designing and manufacturing lower-cost, high-power density servo drives. The company's focus remains to create and deliver the best motion control drives for the brushed or brushless servo motors. By utilizing the latest technology available and providing for the widest range of product solutions, AMC is able to satisfy a wide array of applications across many different industries. Their intention is to provide customers with technical and financial advantages in motion control by offering superior cost-effective servo drive products. From the very beginning, AMC has organized around the principle that people-to-people accessibility and superior expertise is key in helping customers quickly bring great new products to market. I'd also like to thank Electromate. Electromate is the exclusive Canadian distributor for Advanced Motion Controls and specializes in high-performance robotic and mechatronic systems, including servo and stepper motion solutions, positioning actuators, and robots. Electromate's extensive product selection is backed up by its just-in-time delivery and stocked inventory. Electromate also offers engineering assistance and technical support by their dedicated customer service team. Now I'd like to hand it over to Shane to begin today's presentation.
Thank you, Liz, and thank you to everyone joining in this morning and this afternoon for people in different time zones. I'd like to get started here and just kind of focus on what we're trying to achieve today. And really my goal is to get everyone to think about the challenges that we face when we're designing mobile applications. Automation is really, we've seen the last 10 years expanding outside the factory, and when we expand outside of the factory or controlled environment, we are met with a host of new challenges. And a lot of those focus on extremes in the environment, whether that's temperature or shock and vibration. It could be altitude differences. It's also just how do we deal with getting power to the mobile platform or robot. Because the robot has to carry, in most application has to carry its own power source, all while being lightweight and compact. We want to have small bots and allow them to run for a very long time, and with a lot of different sensors and functionality, those all take power, but at the same time we want to make the bot compact and light. So how do we achieve that with today's technologies? And a big piece or enabling technology for that is servo drives. Servo drives and their control capability continue to become more and more intelligent as time goes on. And with that intelligence, we can offload some of the stuff from the controller and help make the overall system more compact, more efficient, and more robust. So what I want to focus on today is how the integral component of servo drive and servo control is, and how it can answer some of these challenges in making mobile platforms. The agenda that I like to cover is really start by just defining what mobile automation is. A little bit. It kind of describes itself. It's taking automation that we traditionally see in a factory setting and moving it outside of that controlled environment, whether that be in a desert, in Antarctica, or in a city, urban environment. There's all different challenges, and we need to think about those when we're designing and concepting our mobile designs. We'll highlight the challenges and kind of lay out what are the pieces of the mobile system and look at those components. And when we look at that, you're going to see it's a very complex system, and if you don't think about that in the beginning, how you're going to lay that out, it could really lead you down a trail where you're not going to come up with an effective or efficient design. The next, I want to move on into the bots that we see out there today and the solutions that advanced motion controls and Electromate can provide, along with other people in the industry, and really how servo controls enable these systems to be functional and achieve the design goals. And then at the end, I want to summarize the applications that we've highlighted and summarize the axes that are under control of servos, and then talk about the technologies. What are the technologies that are enabling progression in the industry today, and then what technologies are still gating our industry. The mobile automation industry is still relatively new in the automation world, and it's not large enough yet to be driving a lot of these technologies. The enabling technologies that we're using today, we're kind of piggybacking off of other industries, whether that's automotive industry or smart device industry, such as tablets or smartphones. Those industries are a lot larger, and a lot of the R&D dollars are going into those industries, but we're using those technologies to enable the progression of mobile platforms. We kind of step back a little bit before we got to mobile automation and look at the evolution of machines. It really started out with people trying to make tasks easier or more efficient, and that started out with hammers and chisels, simple tools of that nature. Even if you look at a mill, using a water-powered mill to grind grain, that was your pre-industrial machines or tools that are trying to make tasks easier for humans or human labor. And then we moved into the industrial revolution as civilizations became more urban and city-oriented, and food was much more readily available. People could focus on going to the store and get food and actually do other tasks during the day, just not making or collecting food. And with that advent, we made these machines, and then we wanted to even make them more automated. And we got into kind of where we are currently in the industrial automation phase. And then in the last 10 years, we kind of moved into taking automation and moving it out of the factory, and that's the piece that we call mobile automation. And if we kind of think about it, farmers were really trying to automate their tasks a long time ago in tractors and combines. Those are mobile platforms. But what we're kind of talking more about is platforms that are electrically driven, not steam or diesel or gas driven. We're talking about electrically driven apparatus in the mobile automation market. And the advent of new battery technology, the efficient power devices and processors has really spawned this marketplace. We kind of contrast the differences between a mobile environment and a factory environment. We look at, on the environment side, the mobile platform has to be transportable, so it's going to see a lot more shock and vibration during even its transport and even during the runtime. Where in a factory, most of the vibration or shock that it sees is actually the machine inducing that onto itself or nearby machines. In the mobile environment, the shock and vibration being transported in a plane, some military vehicle, or even just a standard vehicle driving on the road or a gravel road. A lot of the mobile platforms go to very remote places on the earth. With that, you see large temperature extremes. In your typical factory environment, you see 0 to 40 or 50 C is a standard industrial environment. And that's, element extremes for a factory environment. In a mobile platform, we're looking at minus 55 to 85 C is really becoming the norm for operation now. We have seen applications that we've done down to minus 60 and up to upwards 110 C. So that just continues to evolve. What else you also see from a mobile platform is altitude changes, whether that's deep sea or stratosphere. You have to take in those elements and figure how it's going to impact your design. Because most of the components on a servo drive today are designed for an industrial environment. In the factory, most of your environment is controlled and known. You know throughout the year what the environment is going to be. A big piece to deal with is power. Typically in a mobile platform, your power is finite. You're carrying your power source with you if it's batteries. If you're tethered, you have different things you have to worry about. You can only go so far. You have to worry about carrying the load of the tether with you. In a factory, it's pretty much infinite. It's just an infinite power source. More power can always be had. And on your mobile platform, you're looking at typically lower voltages and DC power, where in a factory you can pick from AC and DC, and you can pick for many different voltages on your AC side. You can select what is best for your application. Your machine interface, typically in a factory, it's going to be hardwired. There's some wireless that's really gaining root in the process control area, but you're typically dealing with a hardwired and a limited range. On the mobile side, you're dealing with wireless or tethered systems. And then lastly, kind of the maintenance. In the factory, you can schedule your maintenance. You have on-site personnel. In a mobile platform, it may not be scheduled. It might be something happened because of the environment that it's in. It's more exposure-based. It's more reactive than proactive. If you look at the components of a mobile system, you can see, there's probably, I got 12 blocks there. You may argue that there could be more or there could be less. Not all systems need all these pieces. But what I'm trying to show here, there's a lot of components that you're trying to put in typically a very compact system. Most of your robots are trying to be as compact as possible, even as light as possible. They need to be transported, and being transported, if you can make it lighter, it's going to be more transportable. Also, it's going to be able to run longer with the batteries that you have on there. On the left-hand side, we have our power management and our power source. and those kind of connect to your servo drives and your controllers. And your controller needs to talk to sensors, whether that be cameras, infrared sensors, proximity sensors on the bot. And the controller needs to have an interface to those different types of sensors. It needs to communicate to your servo drives, and the servo drive communicates or powers the motor and gets feedback from the feedback devices, either to the motor or the mechanics. And the motors are going to drive your traction or propulsion, or your manipulators or steering of your bot. So if I put arrows on here or lines connecting all the different pieces, you can see that's a very complex system. And there are things that we can do to try to alleviate those connections or make those connections easier and more robust. If you put all these components, buy all these components off the shelf, you're going to spend a lot of time designing wiring harnesses. That's going to take up space, and that's going to be cost in your system. If there's ways to combine those things together or get them closer together, that's going to alleviate some of that need for wiring. And every time you have a connection point, that's a point for failure. So the more we can reduce that, the higher quality bot we can make. Now, I want to focus a little bit on the servo control. Really, what is a servo doing? The servo is the drive that controls the motor, whether that be the torque of the motor, the velocity or position of that motor. And that is what controls your axes, whether that's traction or propulsion, steering, or a wrist, shoulder, elbow, or a gripper. That really, at the end of the day, is what is making your bot mobile and able to do tasks. Along with the servo control is you have the servo motor or AC induction motor. And primarily, you're going to be using permanent magnet servo motors, whether that be a stepper or a brushed or brushless servo. For larger loads, for AGVs, you may use an AC induction motor. It really becomes when you want to use something, move a very heavy load, or the bot itself is very heavy, is when you use AC induction motor. The AC induction motor is going to be less efficient than a servo or a stepper, and it's going to be larger, physically larger. One thing that we can do at Advanced Motion Controls is we can deal with low inductance motor and high pole counts or multiple windings in a motor. And another really critical piece in your design is the power. Battery technology has advanced a lot in the last 10 years. It needs to continue to advance going forward. Still today is the big piece. How do we deal with that? We can put a lot of sensors on a bot and run a lot of algorithms, but that all takes energy. And you're always making a compromise in your system on how many batteries you had on there and how many sensors you run on there, or how powerful your processor is. If you had, as the battery technology increases, you don't have to compromise on your sensors or your processing power. So again, this is the enabling technology, but it's also a gating technology. Now, if we look at where are mobile robots being used, well, they're really being used everywhere. We continue in our application engineering group. We get new applications all the time for where somebody's trying to use servo drives in applications outside of a factory that we've never seen before. We've seen mobile automation in homes, office buildings, even your factories, automotive, distribution, warehouses, hospitals. It's a very big piece for mobile automation is hospitals or healthcare. Even on farms where you're seeing bots specifically made for farming. We're also seeing retrofits on your traditional implements. Warehouses, as I mentioned, even parking. Instead of going and finding your own parking spot and a parking ramp, You'll pull up, a bot will come underneath your car and go and park it for you, and when you come back to the ramp, it'll bring your car down to the exit for you to get in and leave. It allows for a much more efficient parking system and more densely, a more dense parking situation. And then also for transportation and for hotels. We're looking at seeing bots used for room service or bringing towels or TV remote to your hotel room instead of having a person come up there. What are the challenges in the mobile automation sector? One is communication. If you recall that slide I showed about 3 slides ago, there's a lot of components in a mobile system or a mobile platform. And how do you communicate between all those subsystems? You also have to communicate between the bot and the controller, whether that's a person using a pendant controlling the bot. They're using some wireless control where they can actually see the bot. They actually may be in a different country or a different state controlling the bot. The bots also need to be able to communicate with each other. So that's a lot of information just there. How do we get all these pieces to communicate together? Is that a proprietary standard, or do we leverage open standards that exist in the marketplace? A lot of the robots are used in, they say dirty, dull, dangerous environments that humans don't want to be in, or they may be critical operations. So the reliability needs to be very high. Talked about the maintenance a little bit. Sometimes it's not scheduled, it's more reactive. So how do we make a design where we can easily pull out the piece that's not working and put in a new piece to fix it? Or how do you make it more modular so that you can have a base platform that's in charge of your traction, and I can put different manipulators or different sensors onto the bot itself to do different tasks. The cost, do you go and design custom assemblies, or can you leverage off-the-shelf assemblies? As bots move out of maybe military or automotive marketplace and get more into the consumer or homeland security, first responder marketplace, the cost needs to be driven down to really meet the price target for the demand. Autonomy, this is always a critical piece for a bot. When it powers up, it's not always powered up, how does it know where it's at? Touched on this a little bit before with the slide. It talks about power. We're always going to be worrying about this power. Batteries are heavy, they're finite, so how can we enable that charge or that potential energy that it carries? How can we make the bot operate as long as possible with that finite charge? So we're going to look at efficiency of the subsystems, and you really have to look at the whole system as one. We can't look at each subcomponent individually. We run into many applications where an engineer will go and design a very efficient motor, and to run that motor we got to add in inductors in front of that, and there you really kind of shot that efficiency. So a servo drive and a servo motor need to be looked at together, and how does that effectively operate? Again, you add a gearbox in. Is there a better way that you can direct drive that? You have to look at the whole system and overall. If you just look at each subcomponent, you're going to potentially not achieve the results that you're looking for. The traction. How do we deal with speed, acceleration, and climbing all in the same system? They're all really kind of fighting against each other. You may want your robot to travel at a rate of 10 miles an hour, but you also need to have it climb stairs or climb a ramp that is going to take a minute long. I can give you speed and I can give you torque in a motor. I can't necessarily give you both. So how do you deal with that? You can do that with higher voltages in your battery supply, or we can do peak current, so it's got to be a finite time where we can climb the ramp or the stairs. How do you get it all, right? I got to look at the motor and drive together. You can do dual windings in your motor, or you could have a gearbox, a dual-stage gearbox. There's many ways to look at it, but again, you got to think about that in the concept and design phase. Environment. This is the big piece. The temperature, shock, the vibration that it's going to see, altitude or depth. It's a very wide operating range. And then lastly, again, we could enable this stuff with the size and weight. We want it to be compact, lightweight. How do you integrate these subsystems together to try to make them a bigger subsystem and reduce some of your wiring, some of your connectorization, and then thermal considerations. I want to put servo drives or controllers in an enclosed environment that's in a very wide operating range. How do I deal with the thermals and get rid of that heat out of there so it can operate? And then cabling complexity. How do we make that simple and robust? Now I want to move into the types of robots that we're going to see or that exist in the marketplace or that are coming online in the marketplace. The first piece that I want to talk about is CoBots. So CoBots is a relatively new term, the term used for collaborative robots. And what that means is you're having robots that are going to work in collaboration or conjunction with a human, whether that be teaming up with a robot to achieve a task, like the picture that I show there in an automotive plant where you have a bot that brings the device to the operator to install in the car. It may be heavy. The robot may allow it to help line it up, and it brings the source material directly to the operator as opposed to the operator reaching over on a bench or a workstation to bring the part over to the vehicle. We've seen in security, so that could be in a museum or an airport or a school. You have bots that will drive around at night to cover a larger area as opposed to paying multiple people to secure a campus. That same bot can also be an information kiosk or greeter during the day, so they can be multi-purpose. Material handling, we're seeing in hospitals where the bots are collecting the laundry and bringing the laundry down to where they can be washed and laundered. Also delivering supplies to the different levels in a hospital. Also material handling in a warehouse. This is really what enables Amazon to do all their two-day shipping to everybody. Inspection. Bots have been used in inspection a lot in a factory. Now how can we use bots to inspect pipelines or power transmission lines, phone lines, all types of things? They can use bots to go and inspect that stuff. You can put a bot in a pipe and have the bot drive through the pipe with cameras on it and give direct feedback to the operator. The next piece here we see was unmanned vehicles. And a lot of this was driven from the military side and oil exploration side. And we're looking at unmanned vehicles, which are UAV and UAS. So those are air vehicles or air systems. You have UGVs, which are unmanned ground vehicles. And the next one is a UUV, which is an underwater vehicle. And a USB is a surface vehicle, which is on the water. Then you have AGVs, which are automated guided vehicles, and then AGCs, which are automated guided carts. Cart and AGV are very similar, where a cart is typically going and it's a tug. It goes up to something else and hooks onto it and pulls that, whether it's a little trailer behind it or it's actually carrying the load on top of it. And then ROV is a remotely operated vehicle. So these are all just types of unmanned vehicles. The last piece that I want to talk about where classification is autonomous vehicles. So that could be a tractor on a farm or a nursery, cars, we keep hearing about these autonomous or self-driving cars. There's a lot of effort being put into making that a reality. We're seeing that in trucks. You could do that for whether that's going to be trucks in a mine, very large vehicles where there's not people around. That's where they're first gaining traction, just like on farms. But buses take a very simple route. They deal with the same route every day. So you're starting to see unmanned systems for that. And then also is retrofits. So a farmer may have a whole fleet of implements and they can't keep up during harvesting, so they can go and actually retrofit systems to allow harvesting to be done automatically. They bring the vehicles to the field or implements to the field, and at that point the implements run autonomously. So if we kind of go in depth more into each one of these robots that I spoke about, I'm going to kind of talk about where servos are used and what those needs are, and some of the solutions that I have seen done to solve the problems or challenges that these bots see. The first is the UGV. This is probably the most intensive from the amount of axes that you see on a bot or a mobile platform. I've seen bots where you have up to 8 or 9 different axes on there. First, you deal with traction. How do you get the bot to move? Is that wheels or tracks? How do you steer the bot? Do you actually have a steering axle, or do you do it by turning the wheels or the tracks in opposite directions? You have a turret. You may have a base platform that is your traction, and you have a turret on top of that. And on top of that turret, you can put all types of different manipulators, and that is joints that could be a shoulder, elbow, wrist. It may not be all of those. It may only be an elbow and a wrist. You may have 2 arms on a bot. And then at the end of the arms, you have manipulators, whether that be grippers or hands, or different sensors or probes. The big needs here are the shock and vibration that the UGV sees, and very compact assemblies. If you kind of think about back to that slide where I showed all the components of a subsystem, and you look at that bot on the picture there, where do I put all that stuff? A lot of that room in that bot is going to be used by the power or the battery system. So where do I put all that stuff? I'm going to have to put some of the servo controls up near where the motors are, and that's going to be in the chassis or in the manipulator arm of the bot itself. And I'm dealing with a lot of axes, so it's going to be a lot of different wiring. So how do I help reduce that? Well, what we can do is merge a lot of these sub-assemblies. Can we combine your servo with the controller? Can we take some of the power management on and put that into one assembly? By merging these sub-assemblies, you reduce your wiring. You can make your connections with traces on the PCB, which are very reliable, cost-effective, and use less space than your traditional connectors and cabling harnesses. And to really make that happen, you're looking at custom assemblies. You're not going to go find this off the shelf. You may find pieces of this off the shelf, but there really are not, manufacturers are not making purpose-built systems for robots. They're making purpose-built components, but not systems today. Show you a couple of examples how we've solved some applications. Both these are 2-axis examples. The one on the right is an example where we're controlling 2 axes of traction, so each side of the bot from a traction side, and we also have control. The manufacturer or our partners, we put their control device directly on that assembly, and so you have your controller, 2 servo axes, and some power management all in one assembly. And you can see it's very compact. It's an integral piece to the bot. It can be simply taken out with 2 screws, They don't have to remove anything else. You can access it directly from the outside of the bot. So it achieves a lot of the, or answers a lot of the challenges that we spoke about earlier. The bottom to the left picture is a 2-axis system there, and that's for camera control, pan and tilt on a camera that can be mounted to whether that's a UAV or a stationary device, or even on a UGV or a subsea vehicle. It's really designed to control a camera where it doesn't matter where the camera is mounted, but it's 2 axes combined together, and it's made for a very wide operating range of systems. 12 volts to 72 volts can be provided to that system, and they can operate in any of those environments. Again, we talked about on the UGV, we see a lot of axes. How do we do that? You do that by combining axes together on one carrier card. And you can do that with what we call embedded drives. So you plug these components that focus on motor control into a carrier card, and that carrier card can be custom built to fit inside your bot. The next piece we want to see is bots that deal with water, whether that's under the water, whether it's tethered, untethered, whether it's on top of the water. And there you're dealing with, instead of traction, with propulsion, control surfaces. So you want to be able to have fins when you're underwater or on top of the water. How do you control the vehicle? A lot of times these have cameras on them. How do you control the camera? And again, you'll see arms and grippers just like you did with UGV. A little bit more what you really need to focus on with these bots is the conformal coating. You're dealing with condensation or high humidity environments, salt water. You're also dealing with very high pressure environments. When you go go deep under the ocean surface, you deal with very high pressures. How do your components handle that? How do you deal with air when it gets compressed? You need to think about that when you're designing that system. Again, you're looking at very compact designs. There's not a lot of room in these bots that go very deep in the water. So much of the chassis is designed to deal with the pressure, so you don't have a lot of room to put in these other components. What I show on the picture on the right are a couple examples of these bots, and then a picture where the drive is sitting actually on the motor in the back end housing of the motor, and that whole motor electronics is sitting in a bath of oil, non-compressible fluid, so they can go to very deep ocean levels and deal with those pressures so that you don't have your components aren't going to be crushed in the pressure. So a good thing that you can do is integrate your solutions for these types of vehicles. How do I put the bot into the chassis? I can reduce the overall volume, the overall weight of the system, and you can put that also into the motor actuator, as I showed in the previous picture. Also on the right-hand side, I show a drive, a servo drive that is in a circular fashion. Again, it's going to be mounted in the back end of the motor. That particular drive there operates from a -40 to 110 C. And not only does it have the servo drive control, it also has the controller and communications front end built into it also. So you're merging sub-assemblies, and you're taking the servo and putting it right in the back of the motor. So all you have is wires going from the drive to the motor phases itself. The feedback is done magnetically, so there's no wiring for the feedback. And only wiring that is coming into the motor drive assembly is power and communication. So you really minimized the wiring that is done or needed for this application, so you achieve a lot of the goals that we've been looking for in a mobile platform. And the other upper picture there is showing a drive. So that the black part is actually a side of the manipulator that you would see on a platform. So you open 2 screws, you unmount the you can pull out the drive assembly. So there's drive and a controller all in one. So that's the robot controller for the arm. It's all built in that one assembly. On the outside is, again, is just going to be power and communication. So we're integrating assemblies, putting those assemblies inside the bot, and reducing our wire count and making a more robust system. Here I want to talk about UAVs or UAS. So these are unmanned air vehicles or systems. What we're looking at here really is, again, how do you move the system, how do you control the system, and I want to put some type of sensors on there, and how can we control those. With the air vehicle, what you're really worried about is lightweight. Weight is all we're focused on. And how do you make your system small? I show a picture of a servo drive here that has an integrated heatsink. There's no piece of metal on it. All the heat sinking is done with internal layers on the drive itself. And how do you deal with your really low pressures and high altitude environments? Again, when you go up in the air, you get lower pressure, you have less air to dissipate your heat into, so you have to worry about your thermal efficiency. You start by making very thermally efficient designs and taking novel approaches to getting that heat away from your power devices and any other critical components. We kind of talked about different applications here for your extended environments. How do you deal with humidity and condensation? You can do that with conformal coating. There's lots of different conformal coating materials out there, and you pick that based on the chemicals that it's going to see or the environment that it's going to be in. Your shock and vibration, you want to keep your components on your PCB low profile as possible. If you can't, a lot of times with capacitors or connectors, you may have to add adhesives or mechanical restraints on those devices. And lastly, pressures. How do you deal with these pressures? Whether it's low pressure or high pressure. In a high pressure system, you can submerge the whole system or your electronics in a non-compressible fluid. That could be oil. And then when you go to a low pressure system, how do you deal with your thermal dissipation? Again, you're going to start with try to make your designs as thermally efficient as possible to begin with. Then after that, there's ways that you can deal with on how to get rid of your heat. Extended temp, this is by far the most requested feature that we see here at Advanced Motion Controls and that I hear in our applications group is how do we deal with these temperature extremes? And we do that by using automotive grade components. And we also deal with high efficiency designs for power devices. Also, how do we keep the system intact? You can, either dust. How do you keep dust or water out? And we do that with plastic cases, gaskets, and connectors. If we look at an AGV and an AGC, I show a picture of an AGC there, and I also show a picture of a servo drive, which is probably 6 inches by 8 inches, and that does 250 amps on a 60-volt bus. When we're dealing with AGVs or AGCs, we're dealing with very large loads, and to do that, we need to have a lot of power, large currents, but also need to be very, very compact. This is the market where you'll see not only permanent magnet, but also AC induction motors. So what we can do on the drive side is make it very compact, and how we do that is we can leverage a lot of the metal that is the AGV and the AGC to dissipate the heat that's generated from the drive itself. So that drive that you see in the picture can't operate by itself in air. It has to be mounted to a considerable chassis member on the AGV. And that is allowed because AGVs or AGCs are built with a lot of metal. They're very sturdy. They carry very heavy loads. They carry a lot of batteries, so they need to be very sturdy and strong themselves. And the last pieces we want to talk about is how do you make your system more efficient from a processing standpoint? Well, the servo drives have a lot of built-in capability already in them. So if you can offload some of the processing needed at the control level and push that down to the drives, you can pick a lower end processor and more thermally efficient processor for the controller. You distribute all the motion control down to the drives, whether that's jogs, indexes or homes, or even having sequences or programs inside the drive itself. And that really just allows you to reduce your part, be more, your part count more efficient from an energy standpoint, and it just saves in the volume overall of your system. Now I want to talk, we got about 13 minutes left to keep us under our hour, and I want to have a few summary slides, and then we'll take questions. Application summary, where are we seeing these applications? It's military, homeland security, agriculture. We see a lot of it in research. We see bots being used in research in ocean depths that we can't get to, volcanoes, surveillance, reconnaissance, medical and healthcare, and then first responders. You can see there's a very wide range, and we've talked about that. For mobile automation, it has a lot of different challenges that it needs to answer, and each application may have some unique challenges that other ones do not. Where are we seeing servos? We see those in cameras, moving the bot, whether that be propulsion for water vehicles or air, traction for ground vehicles, the different type of manipulators that you see. You can see in the pictures that I have on the right, there's all different types of arms and sensors on these bots and different ways to get them to move. You have grippers, fingers. Each finger has a lot of different joints to move. You have your shoulder, elbow, and wrists. So there's a lot of places that servos can be used. In each one of those axes, you have processing power that can be leveraged. What are the enabling technologies today? So this is kind of a snapshot of where technology is in the mobile automation market. The power devices, the size has come down considerably. They're very efficient from a thermal and a power standpoint. The processors, again, the size has come down remarkably in the last 10 years. Very fast, very efficient. There's a lot of low power modes that they operate in. So when the bot is in operating but it's currently not doing anything, the controller or the processors can go into these low operating modes where they're using very little energy, and then they'll wake up on a command from the operator. We have battery technology. This is enabling, but it's also gating. The power density has improved greatly. The cost has also come down. Materials, what kind of materials can we use to make the vehicle very lightweight and still achieve the strength and robustness that is needed? Intelligence, there's been a lot of work done in localization and autonomy and on sensor algorithms to deal with all the different types of sensors. There are so many sensors out there today that we can use, but we still have to interpret that data. The sensor just simply collects the data. The processor or controller has to analyze that data to make decisions for the bot. What are the gating technologies? So this is an area that still needs a lot of work to progress the mobile platforms, and that's really the power density of batteries. If you compare a pound of battery versus a pound of gas, you can see there's a lot more energy in a pound of gas than there is a pound of batteries. But our mobile platforms are being used by batteries, so how do we progress that? The data analysis. We have all these sensors that can collect tons of information about its environment around it, but how do you effectively analyze that data without having to put a bunch of processing power on there? Can we have processors that use limited amount of energy but can do a lot of computation? Mechanics. A lot of mechanics today we're still just stealing from the industrial automation market, for stuff that was designed for a factory, not designed for a bot. Along with actuators, can we make things, or are there going to be manufacturers out there that make these actuators and motors specifically for the mobile automation market? Pattern recognition, remote operation. A lot of these remote operation is very proprietary. There's not a lot of open standards that have been adopted yet. So each system is very proprietary. How do you make our bots more modular, scalable? And that happens through standardization of communication between subcomponents. Sensor integration. Can we integrate some of these sensors into the devices as opposed to just making them off-the-shelf component that you bolt onto the system? And then mapping, exploration, and autonomy. Again, how do we get that data in and effectively analyze it and make decisions efficiently? So the kind of what I was highlighting in my presentation is why are servos critical to mobile platforms or robot designs. And if you go back and look at the challenges we presented in the beginning, it really comes down to size and weight, power and efficiency, and the environment. Servos allow the robot to be smaller overall. Servo motors are very compact when compared to other motor technologies, and they're very efficient. Servo drives are efficient. Servo drives today can be effectively inserted into the back of the motor or next to the load. You do not have to have a dedicated enclosure for the servo. Just mount the servo in the motor or inside the bot. It's the most efficient way to move your bot, and with that allows your bot to operate longer with its finite battery source. The environment, there's a lot of components made for servo drives that allow it to operate in very extremes of temperature, shock and vibration, humidity, and pressure. We talked about earlier in earlier slides on how we can deal with those extremes in those environments. And then lastly, why servo drives from AMC? We deal with custom solutions. We have 30% of our market is ground-up customs. 40% is standard off-the-shelf. The other 30% is some type of modification of the standard. So we really have solutions that fit the needs for robot manufacturers. And we do that with compact design, lightweight designs. So really, how do we put a lot of power and a lot of intelligence in a small space? And that's done with power efficiency, adding capability to a drive beyond just controlling the motor, and then configurability. Allow the user to configure the system to meet their needs of their particular application or that particular axis on the bot itself. So I'd like to thank you for taking time out of your day to listen to the presentation. And this would be the time if you have questions that you've put in the chat to Liz. So Liz, is there any questions?
Thank you, Shane. And we are, like Shane said, we are accepting questions. So go ahead and put any in the chat. We will only have time for a couple questions since we're running kind of short on time here. But I'll go ahead and ask one of our first questions. How do you control motors with low inductance?
So motor manufacturers are trying to make their motors as efficient as possible, and they use models to develop these motors. And a lot of those models will lead them down a path where they have a very low inductance to achieve the efficiency goals of the motor design. And when you couple that with a servo drive, the servo drive needs inductance in the motor to operate because it's a switching device. And for servo drives to be able to operate with that, you can do that by adding an inductor in between the drive and the motor, but you're really defeating what you just tried to achieve on your motor design. We're effectively just adding inductance back into the system, and we're just going to waste energy running current through those inductors. So what you can do on the servo drive side is you can increase the switching frequency, and you can drive that from instead of your traditional 20 kilohertz drive up to 100 kilohertz. Somewhere on a larger motor, maybe down 40 to 60 kilohertz. But you really do that by increasing your switching frequency on the drive and how you switch your power devices that deal with low inductance motors.
All right, we have another question from the audience. What is the maximum efficiency achieved for servo drive for these kind of applications?
So on axes where you're dealing with manipulators on your lower power, you're going to be, and it's dealing with a permanent magnet brushless motor, you're going to be upwards of 98%. And on your larger axes where you're doing traction, you're going to be 95%. With AC induction motor, it's going to be a little bit lower because in AC induction motor, I don't have permanent magnets on the rotor. I actually have to create that magnetic field. So I'm going to waste some energy on creating that magnetic field. So you're going to be probably in the low 90s for the overall system. So it's really dependent on your drive and your motor and your mechanics that are driving the load. But from the drive standpoint, on small, lower power axes, so I'm talking probably under a kilowatt, you're talking 98%. Stuff over that, it's going to be 95% or higher.
All right. Thank you again, Shane, for that informative presentation. And thank you to all our participants today and to our sponsors, Advanced Motion Controls and Electromate. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. All questions submitted through the webinar screen will be answered by email after the conclusion of today's webinar. Be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Thank you and have a great day.